Hello and welcome to another video on calculus on the chapter limits. In this video, we are going to discuss about continuity. So a function f of x is continuous at a if the limit of f of x as x approaches a equals to the value of the function at a. So if f is not continuous at a, then we say that f has a discontinuity or f is discontinuous at a. So in order to check whether a function is continuous or not continuous at a given value a, what we are going to do is we are going to check these three conditions. The first one is the function is, we make sure that the function is defined at a, or a is in the domain of the function. The second condition is the limit as x approaches a f of x exists. And then the third condition is the value of the function is same as the limit. So the function is defined, the limit exists, and the value of the function is same as the limit. So if these three conditions hold, then we can say the given function is continuous at a given value a. So let's check that with a graph. So we are going to identify where the function is not continuous or where is the function discontinuous, and then we are going to classify the discontinuity. We have mainly three types of discontinuity, and we are going to classify this. So the first one, we see that the function is not continuous at 3, because at 3 we have a function, the value of the function right here, and then in this case, if you're asked why is the function not continuous, because the limit does not exist. So the left hand limit is -1 and the right hand limit is 3, so the limit does not exist. That's why the function is not continuous here. So f of x is not continuous at x equals 3. And the type of discontinuity here is called the jump discontinuity. So jump discontinuity, which means the function jumps. So function goes here, and then from here the function jumps up to a value of 3. So that's why it's called a jumped discontinuity. The second one, the function is defined. We have the value for the function. The limit also exists. So the limit as x approaches 3 is -4. But here, the limit is not same as the value of the function at x equals 3. So the function is not continuous at x equals 3. Okay, so f of x is not continuous, or it's discontinuous. We can also write discontinuous. Okay, it's not continuous at x equals 3 again, and this type of discontinuity is called removable discontinuity. The reason that we say that is we can redefine this function such that we can move this value right here at the hole, and then we can make the function continuous. So we can redefine the function, and then we can make the function continuous. So that's why it's called the removable discontinuity. We can remove this type of discontinuity. Usually if there is a hole and the function is defined somewhere else, so in that case we can redefine the function and make it continuous. So the third one is the function is not continuous at -5. Here, the same thing, the function is not defined. So the first condition is this condition is not hold here. So f of x is not continuous at x equals -5. This type of discontinuity is called infinite discontinuity. Usually when we have the vertical asymptote, where the function goes to infinity. So those points where the function is discontinuous and the function goes to infinity or have a vertical asymptote, we call that as infinite discontinuity. So that was from the graph, which is easy to see from the graph, and then we were able to figure out that. Now, when we are given the function, the formula for the function, how do we determine the whether the function is continuous or not? So for that, we are just going to look at these three conditions again. So we'll check that. We'll go through 1, 2, 3, and if just one condition is not satisfied, then it's not continuous. For the function to be continuous, all three conditions must be satisfied. So for the first one, so let's go ahead and see if the function is defined at x equals 5. So if I plug in x equals 5, okay, in the numerator I get -1, but when I put it in the denominator I get 0. So when I substitute x with 5, I'm going to get -1 over 0, which is undefined. So the function is not defined at x equals 5. So that means f of x is not continuous at x equals 5 because f of 5 is undefined. So that's it. If it does not satisfy one of the conditions, then we don't have to check the rest. It's not continuous. Now let's look at the second example. So for this one, if I plug in 5, I get 25 times 5, which is 125 divided by 5 squared plus 25. So g of 5 equals 25 times 5 divided by 5 squared plus 25, which gives us 125 divided by 50, and that is 5 over 2. So that means the function is defined at 5. Now let's go in and check the second condition. So let's go ahead and find the limit. So limit as x approaches 5 of 25x over x squared plus 25. Again, we can do direct substitution for the limit here because the denominator is not equal to 0. So we get 125 divided by 50, and which is 5 over 2. So the limit exists. That's the first condition. This is the second condition. The third condition, now the value of the function is 5/2 and the limit is also 5/2. So limit as x approaches 5 of g of x equals g of 5. That means this implies that g of x is continuous at x equals 5. So it satisfies all three conditions. So it is continuous at x equals 5. So let's look at this one. So the first thing, let's see whether the function is defined at x equals 0 or not. So just be careful here again. We are looking at the piecewise function. So I know you're familiar with piecewise function. So we have a 0 here. That's where we are looking at. So if x is less than 0, or if x is on the left of 0, then we are going to use h of x equals -2x plus 1 as the function. And if it is on the right of 0, then we are going to use h of x equals -x squared plus 2x minus 2. Now the first thing is, let's go ahead and find if the function is defined at x equals 0. So can we find h of 0? And then to find h of 0, we have to use this second piece of function because 0 is included here. So we have -0 squared plus 2 times 0 minus 2, and that gives us h of 0 equals -2. So we have the first condition, that is, the function is defined at 0. Now the second condition, we need to find the limit. Since this is piecewise function, so we cannot just find the limit when x approaches 0. We have to see left and right limit here. So let's go ahead and find So this is number one. So number two, let's check the limit. So let's go ahead and find the left-sided limit first. So limit as x approaches 0 from the left. So remember, we did this type of problem. So when x approaches 0 from the left, okay, so we have to use this function to determine the limit. So it's negative 2x plus 1, which is when I plug in 0, I get 1. So that's the left side limit. Now let's go ahead and find the right side limit. So limit as x approaches 0 from the right of h of x. So when x approaches 0 from the right, we have to use this definition or this definition of the function. So it is negative 0 squared plus 2 times 0 minus 2. Sorry, let me write this way again. So we are going to use this definition, negative x squared plus 2x minus 2. So when I plug in 0, I get negative 2. So the left-hand limit is 1, right-hand limit is negative 2. That means limit as x approaches 0 of h of x does not exist. So that means this function does not satisfy the second condition here. So which means h of x is not continuous at x equals 0. Now this problem, I want you to pause the video and try this on your own, and then you can go back and check your work. So let's go ahead and do it. Now, let's go ahead and check the first condition. Is f of a defined, or is the function defined at x equals 2? So this is where we are checking the continuity, okay? So the function f of x equals 3 if x equals 2. That means the function is defined, and the value is 3. So f of 2 equals 3. So that's the first condition. The function is defined, and the value of the function at x equals 2 is 3. Now let's go ahead and check the limit. So again, for this one, we have to use both side limit because this is a piecewise function. So again, on the left of 2, we are going to use this function. And for the right of 2, we are going to use this function. And at x equals 2, we have 3. So let's go ahead and find the left-hand limit. So for the second condition, we're going to check the limit. So limit as x approaches 2 from the left of f of x equals limit as x approaches 2 from the left of 2x plus 1. So when we plug in 2, we get 2 times 2, 4 plus 1, this is 5. So that's the left side limit, okay? Now let's go ahead and check the right side limit. Limit as x approaches 2 from the right of f of x equals limit as x approaches 2 from the right of, so for the right side limit, we have to use these functions, so negative x plus 7. So now when I plug in 2, I get negative 2 plus 7, which is also 5. So this shows that the limit exists, okay? And the limit as x approaches 2 of f of x equals 5. So the first and second conditions are satisfied. Now let's go ahead and check the third condition. So the limit must be equal to the value of the function for the function to be continuous. But here, the value of the function is 3 and the limit is 5. So this implies that limit as x approaches 2 of f of x is not equal to f of 2, which says that f of x is not continuous at x equals 2. Now we have a theorem which says that a polynomial function is continuous for all x, or it's continuous on its domain, which is negative infinity to infinity. That means a polynomial function is always continuous, so we don't have to check the continuity of a polynomial function. A rational function is continuous for all x except when the denominator is 0. So there could be two cases when the denominator is 0. One is the function might have a hole, or the function might have a vertical asymptote. And we have checked that earlier when we did the limits. Yeah, when we did the limit. Okay, so you have a vertical asymptote when you are trying to find the limit and you cannot cancel the common factor, and then the limit is infinity. You will have a hole when you try to find the limit of rational function and you are able to cancel the common factors on the numerator and denominator. So that's where we have a um, discontinuity of the function, okay, where we have a hole or the vertical asymptotes. So now, for it says for what values of x is the function f of x equals x over x squared plus x minus 6 continuous? We know that this is continuous for all x except whichever value make that denominator 0. So now we can write this as, so this is a rational function. So f of x is not continuous for all x such that x squared plus x minus 6 equals 0. Okay, so all the x value that make the denominator 0. So at those x values, the function is not continuous. So let's go ahead and solve this equation. So we can factor this as x plus 3 times x minus 2 equals 0. And that gives us x equals negative 3 and x equals 2. So the function is not continuous at x equals negative 3 and x equals 2. Or we can write f of x is continuous for all x except x equals negative 3 and x equals 2. Or we can also write the intervals where the function is continuous. So the interval where the function is continuous are these intervals. So negative infinity to negative 3, negative 3 to 2, and 2 to infinity. Now, we could have a function which is continuous from right, just like right limit and right-sided limit and left-sided limit. So we could have a function which is continuous from right or continuous from the left, especially at the end point. So when we're talking about a function and the function stops here, so we can say this function is continuous from the left, or at this end point, the function is continuous from the right. So when you go from the right, the function is continuous. So that's what one-sided continuity means, okay? So if the limit as x approaches a from the right is equal to the value of the function at a, then we say the function is continuous from the right, okay? If the limit as x approaches a from the left equals to the value of the function at a, then we say the function is continuous from the left. So a function is continuous over an open interval if it is continuous at every point in that interval. So let's see where this function is continuous for which interval. So first thing that we need to use here is the theorem that we just looked over here. Okay, so this theorem right here. Say polynomial function is continuous for all x on its domain. Okay, so here this is a quadratic function, or it's a polynomial function. This is a linear function, or it's a polynomial function. So we can say that f of x consists of two functions. Okay, so here f of x consists of two functions. That means f of x is continuous for all x. And then we cannot say anything about, we have to check for this point, okay, for this x value, -1. So we'll say f of x is continuous for all x except -1. And then we will check this one. So we will check at x equals -1. Okay, so just looking here, on the left of -1, this function is continuous because it is a polynomial. On the right of -1, this function is defined and it's continuous. Now we'll check what happens at -1. Okay, so let's do this. So let's go ahead and find the value of the function at -1. So the first thing we are going to find f of -1. So to find f of -1, see equal sign here, so we'll use this one. So -1 is squared plus 1, which is 2. So f of -1 is 2. Now let's go ahead and find the left-hand limit. So limit as x approaches -1 from the left. So we'll use again this one, which is, okay, let's write f of x equals, so -1, sorry, -1 squared plus 1, which is 2. Now the value of the function is same as the limit, so this implies that f of x is left continuous at x equals -1. So it is left continuous at x equals -1. Now let's go ahead and check if it is right continuous at x equals -1 or not. Okay, so again, f of -1, it does not change, it's still 2. We still have that one. Now let's go ahead and find limit as x approaches -1 from the right, okay, of f of x. So when it approaches -1 from the right, we have to use the second piece of the function. So 3 times -1 plus 2, which is -1. And this is not equal to the value of the function, because the value of the function is 2, but the limit is -1. So this implies that f of x is not right continuous, okay, at x equals -1. So it is left continuous at x equals -1, but it's not right continuous at x equals -1. So this is how we write. So the function, the intervals where the function is continuous. So f of x is continuous on, so -infinity to -1. It's included because it is left continuous at that value, and then from -1 to infinity, this is not right continuous, so we have to use that parenthesis. Okay, so again, this is a try now example. It's just like the one that we did. You can pause the video, try this one, and then turn on the video, resume the video, and then check your work. Okay, so let's go ahead and do the same thing again. This is a polynomial function, 3x and x squared plus 4x. That means f of x consists of two polynomial functions which are continuous for all x values, except at one we have to check. Okay, so f of x is continuous for all x, okay, except at x equals 1, which we will check. So we'll check at this point, okay? So now let's go ahead and do the same thing. Let's go ahead and find f of 1. So what's the value of the function at 1? Equal sign here. That means we use the second piece, which is 1 squared plus 4 times 1, and that is 5. So f of 1 is 5. Okay, so now let's go ahead and find the left limit. So limit as x approaches 1 from the left of f of x equals, so for the left, we use this one, which is 3 times 1 and 3. So here, the value of the function, so this implies that f of 1 is not equal to the limit as x approaches 1 from the left of f of x, which means f of x is not left continuous at x equals 1. Now let's go ahead and check if it is right continuous at x equals 1. So let's go ahead and find the limit x approaches 1 from the right of f of x. So when x approaches 1 from the right, we have to use the second piece of the function. So 1 squared plus 4 times 1, which is 5. And that equals the value of the function at 1, which is 5. That means this implies that f of x is right continuous at x equals 1. So therefore, we can say that f of x is continuous on the interval. So from negative infinity to 1, and it's not left continuous. So we have that parenthesis, and from 1 to infinity, we have this bracket because it is right continuous on that interval. So that's the interval where f of x is continuous. Now, here we are asked to determine the value of b such that the function is continuous everywhere. Okay, so again, it's very similar to the previous question. 4x plus 2, this is a linear function, this is also a linear function. So they are continuous everywhere. The only point where they could be discontinuous is this point. Okay, so for example, this is a line with a positive slope, so it might look something like that. And then there we have that less than or equal to sign, so you have a dot here. And this is a line with a negative slope, so you might have something like this. Okay, so if this happens, then it is not continuous at -1 because the function, the left hand limit and right hand limit are not same. The limit does not exist, so it does not satisfy all the conditions. So, but what could happen is if this graph looks like this. So this is a left side graph. There's a dot, and then we have the right graph just starting from the same point. Then this is continuous because there's no break now. There's no hole because of that dot. That happens only if this value of this blue line or this function 4x plus 2 equals to the value of the function here at x equals -1. Okay, so now we can write f of x. Okay, so f of, we already know it's continuous everywhere except at -1. So f of x is continuous at x equals -1 if 4x plus 2 equals -2x plus b at x equals -1. So the first thing what we are going to do here is we will plug in x equals -1 and then find the value of b. So this implies 4 times -1 plus 2 equals -2 times -1 plus b. So 4 times -1 is -4 plus 2 is -2 equals 2 plus b. Now if we subtract 2, we get b equals -4. So if b equals -4, then this piecewise function is continuous everywhere. So it's even continuous at -1. So now we have another theorem. This says that if we have a root function, a function with radical, okay? So if n is odd, or if this is odd root, okay, then the function is continuous at all points where f is continuous. So it's continuous in the domain of f of x. But if n is even, then the function is, we can guarantee that the function is continuous at all values of f, and there's a condition or restriction that f of x must be positive. The reason is we cannot have a negative inside the even root because that does not give us a real number. Okay, so that's what we are going to look at next. We might have some example for that here. So let's see what we have. Sorry, here. Now again, this is a function under the square root. We have an even square root. So that we have an even root. So that means we are going to say that this function f of x is for sure continuous if 16 minus x squared is greater than 0. Okay. Now this implies that 16 is greater than x squared, or we can also write x squared is less than 16. Now if we take the square root, we get absolute value of x is less than 4, which means x is between -4 and 4. Now if you graph this function, the graph of this function looks like this. So we have -4, we have +4, so it's like this. It's a semicircle. with radius 4. Okay, so that's how it looks like. So this says that it's continuous in the open interval from -4 to 4. Now what we need to do here is we need to check the endpoints, okay, whether the function is continuous at the endpoints or not. So what we need to do is the value of the function at the endpoints and the limit. That's what we are going to check. So we know that f of 4, so let's do -4 first. So f of -4 equals, if I plug it in, so I get a 0. So we are checking at this point. So at this point, we are not going to check left continuity because there's no function on the left side. So what we are going to check is the right continuity. So when x approaches to that point, or when x goes to -4, is the function continuous from the right, okay? So for that, we need to check limit as x approaches -4 from the right. Does it exist or does not exist? So now let's see, when x approaches -4 from the right. So these are the numbers that we are looking at. So these numbers are 3.999, it's -3.999 something, which is close to -4, but it's like 3 point something, right? So when we square this number, it is less than 16. So x squared is less than 16. So 16 minus a number which is less than 16, we still get a positive number, or the limit exists. Okay, it's not negative. So that means we can plug it in, and if we plug it in, we get a 0. So the function, the value of the function is same as the limit. That means f of x is right continuous at x equals -4. Similarly, we can go ahead and check if the function is left continuous at x equals 4. So again, let's go ahead and find f of 4, which is 0. And then when x approaches 4 from the right, sorry, here we are going to check the left continuity, sorry. So what we are going to check is when x approaches 4 from the left, these numbers are 3.999, which are close to 4, but they are less than 4, okay? So that means when we plug it in here, so limit x approaches 4 from the left of 16 minus x squared, so this limit is 0. So that means the value of the function is same as the limit. So that means f of x is left continuous at x equals 4. That means f of x is continuous on the closed interval from -4 to 4, because this is right continuous and this is left continuous. So here's another example which is very similar. We are going to do the same thing. So g of x is continuous if 2x squared minus 16 is greater than 0. Now if we add 16 on both sides, so we get 2x squared is greater than 16. Then divide by 2, we get x squared is greater than 8. And then when we find the square root, we get absolute value of x is greater than 2 square root of 2. Now what does that mean? So absolute value of x greater than 2 square root of 2 means this is 0, this is -2 square root of 2, this is +2 square root of 2. This means x are the numbers whose distance from 0 is greater than 2 square root of 2. So that means x values are right here and right over here. Okay, so that means this function, if we graph this function looks like this. So we have -2 square root of 2, +2 square root of 2. So this function looks like this. It goes like that. Okay. So the function is continuous. So this interval is -2 square root of 2 is less than x is less than 2 square root of 2. So we know that it's continuous on that open interval. Okay. Sorry, it's not that one. It is this. So from here, it's these values. So x is less than -2 square root of 2 and x is greater than 2 square root of 2. Okay, so that is the interval. We know that. Now we will check at the endpoints. Okay, so let me draw that graph again. So -2 square root of 2, 2 square root of 2. So the graph looks like this. So at this point, we are going to check the left continuity, okay, and at this point, we are going to check the right continuity. So we know that f of negative 2 square root of 2 equals, if we plug it in here, we get 0. Now limit as x approaches negative 2 square root of 2 from the left. Again, when we approach there from the left, these numbers are in magnitude, these numbers are greater than 2 square root of 2. Though they are negative in magnitude, these numbers are larger. So when I put it here, I don't get a negative number. That means that limit exists, okay? And then I can, sorry, this is not f of x. I always do that. This is g of x. So now that limit is 0. That means it is left continuous. So left continuous at x equals negative 2 square root of 2. Similarly, if we find the limit as x approaches 2 square root of 2 from the right here at this point from the right, we get same thing when we approach there from the right. Those numbers are larger than 2 square root of 2. So when we plug it in here, we don't get a negative number. That means we can do direct substitution, and that gives us again 0. And the value of the function at 2 square root of 2 is also 0. So, sorry, it's g of x, okay, not f of x. So g of 2 square root of 2 is also 0. So this says that it is right continuous at x equals 2 square root of 2. That means g of x is continuous on, so g of x is continuous on the interval negative infinity to negative 2 square root of 2. So since we have left continuity, we have a bracket and 2 square root of 2 to infinity. Everywhere here, okay? So that's what where the function is continuous. Now the continuity of composite function. So if g is continuous at a and f is continuous at g of a, then this composition is continuous at a. Okay, so if the inside function is continuous at a, and if the outside function is continuous at g of a, the y value of g, and we can say the whole function is continuous at a. It's just like finding the composite the value of the composite function. Okay. Now this says where is the function h of x equals natural log of 1 plus sine x continuous. So the first thing, this is a continuous function. It's continuous everywhere in its domain. Natural log of x is also continuous everywhere in its domain. So both of these functions are continuous. But what is the domain of natural log of x? It is only the positive number. So natural log of x, or ln of 1 plus sine x, is continuous. Okay, this is continuous only if 1 plus sine x is greater than 0. So this is continuous and is defined, okay, if 1 plus sine x is greater than 0. Okay, otherwise it's not defined. So now, which means if 1 plus sine x is greater than 0, then this function is defined. Okay, then we can say this implies that natural log of 1 plus sine x is undefined if, from here, if sine x equals negative 1. Because if sine x equals negative 1, then we get 1 plus negative 1, which is 0. So the function is undefined because this is defined only if this is positive, if it's greater than 0. Okay, so that means now we need to find where, at what x value is the sine of x negative 1. So if you just look on your unit circle, this value is 1 comma 0. This value right here is 0 comma 1. This is negative 1 comma 0, and this is 0 comma negative 1. So sine means y value. So sine is negative 1 at this value right here at this point, which is 3 pi over 2. Okay, so that means sine x is -1 at 3 pi over 2, but not just at that point, because that's this angle is 3 pi over 2. But if I go one more round, I come to the same angle, and I keep going round and round and round, so I have infinitely many positive angles. Similarly, if I go counterclockwise, okay, sorry, if I go clockwise, then I get negative angles, which are which have the same value as 3 pi over 2. So now from here we can say, okay, so this is undefined if sine x equals -1, which implies that x equals 3 pi over 2, and not just 3 pi over 2, but if I keep going round, so every after 2 pi, I get to that same point. So I write 2 pi times n. So when I take n equals 0, I have 3 pi over 2. When I take n equals 1, I have 3 pi over 2 plus 2 pi. That's the second round that I'm making, and then that keeps going on. Not only that, if I move on the opposite direction, okay, if I go clockwise, I start generating the negative angles. So I can also write negative here. So 3 pi over 2 plus or minus 2 pi n, those are the those are the x values where sine x is -1. And those are the x values where the function natural log of 1 plus sine x is not continuous. So now we can write natural log of 1 plus sine x is continuous everywhere, okay? Sorry, is continuous for all x except x equals 3 pi over 2 plus or minus 2 pi n. So except this value, it's continuous everywhere. Now, with the continuity, we can also evaluate the limit. So if we have a composition function, again, f of g of x, okay, and if f is continuous at L, where L is the limit as x approaches a of g of x. So if f is continuous at the limit of the inside function, then finding this limit of the composition is just finding f of the limit of the inside function. Okay, so that's how we can find the limit if f is continuous at the value where at the limit of g of x. Okay, so let's look at an example for this. So here, if natural log of x is continuous at the limit of this inside function, then we can just evaluate this limit as the natural log of whatever the value of the limit of inside function is, which means basically what we can do here is we can put this limit inside. Okay, so this equals natural log of limit x approaches 0, 5 sine x over x. And then that equals natural log of limit. So we can factor that 5 out. So we have limit, okay, limit x approaches 0 of sine x over x. And we already know the limit of sine x over x. We have done that using a table and graph in section 2.2. So that limit is 1. So this equals natural log of 5 times 1, which is 5. And then if you want, you can put it into the calculator and get a decimal value, but I'm just going to leave it right here. Similarly, here, this is a square root function. Okay, so square root function is continuous everywhere. So that means I can evaluate the limit of this composition function first by evaluating the limit of the inside function and then finding the value of that function. Okay, so this equals, we can write it limit as x approaches 1 of, so I can factor the numerator, which is x plus 3 times x minus 1, and then divided by x minus 1. I can cancel this one, so that limit equals, so limit x approaches 1 of x plus 3, and I can do the substitution, which gives me square root of 4, and that is 2. So for the continuity, all these functions, okay, like trigonometric functions, the inverse trigonometric functions, exponential functions, logarithmic functions, all these functions are continuous in their domain. So they are always continuous. There's no break, there's no asymptote for these functions within their domain, okay, they are always continuous. Now, the last thing that we are going to talk about here is the intermediate value theorem. So, which states that, let me draw a graph here and then I'll explain it. Sorry. So, this theorem says if we have a function, let's say f of x, and we take a x value here, let's say is a, let's say this is b. Now, what this says is if f is continuous on the closed interval from a to b, and n is a number between f of a. So f of a is right here. So this is f of a. And then let's say this is f of b. Now if n is a number in this interval within here, okay, then there's at least one number c in between a and b. So there must be at least one number here in between a and b such that the corresponding value of the function at c equals this n. So f of c equals n. That's all this intermediate value theorem says. So the only condition here is the function must be continuous on the interval ab, the closed interval ab. So let's look at an example. So this is so that a function f of x equals x squared takes on the value 8 for some x between 2 and 3. So we know that x squared is a graph like this. Okay. So if we have a 2 here, if we have a 3 here, then what this is saying is, so this is f of 2 and this is f of 3. So there must be a number between f of 2 and f of 3. There must be a number here, which is 8, such that, and there must be a number here, c, so that the value of that number at, the value of the function at c is 8. That's what this is saying, okay? So this x squared is continuous in the interval 2 and 3. So f of x equals x squared is continuous on 2 comma 3, close interval 2 comma 3. That means by intermediate value theorem, we know that, okay, there is a number c in between, okay, so c between 2 and 3, sorry, 2 and 3, such that f of c equals 8. So f of c is c squared equals 8. This implies that c equals positive or negative 2 square root of 2 because it's square root of 8. We cannot have negative because we are assuming that c is between 2 and 3, so it has to be positive. So this implies that c equals 2 square root of 2. And then let's check 2 square root of 2. If we put this into the calculator, we get 2 square root of 2 is 2.82 and some more numbers over there. So that means this number is in between 2 and 3. So this is in between 2 and 3. Okay, so that means we showed that there's a number between 2 and 3, which is 2 square root of 2, whose value is 8. Okay, whose values is between. So we can also verify that. So is that value 8 between f of 2 and f of 3? Yes. So because f of 2 equals 2 squared, which is 4, and f of 3, which is 3 squared, and that is 9. So 8 is between 4 and 9. It is between f of 2 and f of 3. And then we got a number c, which is in between 2 and 3. That means we showed what we are asked to verify. That's all for this video. I'll see you again in the next video.